So this video here is the most important one for you guys if you want to do the assignment this week. Here we talk about how we find a matrix equation that we use to solve this through the finite difference route. So let's just start by drawing up what we know here. For 0, we know that y of 0 equals alpha. So y of 0 equals alpha. And in the right endpoint L, we know that y of L is equal to beta. And the way we discretize this problem and construct a grid, as I mentioned earlier, is I start in x0 equals 0, and then I have x1, x2, etc., etc. And here I have xi, and the point after xi, well, we call that xi plus 1. And we call the point after xi minus 1. And between 2 points on the x-axis, these 2 time points, we have a step size h, and the last point is indexed by n plus 1. So all in all, we have n plus 2 points. And what we want to do is we want to be able to find out which values y obtain over this interval in the points x1, x2, x3, and so on by using a finite difference method. And the finite difference method that is constructed in the book for this problem is one that uses center difference formulas. And the finite difference method is written up first just in loose form, or what you can call it, as ci plus times yi plus 1 plus ai times yi plus bi times yi minus 1 is equal to h squared multiplied by f of xi, where f is known based on the differential equation. Okay, and also it has the boundary values y0 equals alpha and yl equals beta, which are also given directly in the problem. So what are ai, bi, and ci? Well, according to the book, ai is given by minus 2 plus h squared x q of xi, and bi is given by 1 minus h halves multiplied by p of xi, and ci is given by 1 plus h halves multiplied by p of xi. So ai, bi, and ci are all known values that we can just get directly by looking at whichever differential equation we are given and reading off the coefficient functions in front of y prime and y. So basically, when you see this, don't be too scared. Basically, what you have is something like 2yi plus 1 plus a half yi minus not a half yi. Yeah, well, yeah, why not? A half yi and then minus 3 yi minus 1 is equal to h squared multiplied by 42 or something like that. So ci, ai, bi, and f of xi, is that true? That's what they wrote, f of xi? Well, the book is a little, oh no, it's not inconsistent, f of xi, yeah. So these things are all known numbers. And just note that this f is not the same f as those f's that we were looking at in the first chapter. So these are two different f's. This f is a completely known function that you can just read off your differential equation. Okay, so then there is quite a jump from this notation where they say that these i's go from 1 all the way up to n plus up to n. There's quite a jump from this notation to another notation on the page after, on page 49, where the book says, well, in order to find the solution by using these equations, we need to turn it into a matrix equation system, A, Y equals Z. Boom. Well, then you sort of think, well, that's quite a stretch. How did they go from there to there? And well, the Y, and if you look in the book, well, A is a tridiagonal matrix. So look at page 49 where when you're watching this video. Look in the book. Then they tell us what A looks like, what Y looks like, and what Z looks like. So let's just, for fun's sake, let's try to write up this differential equation system. Not this differential equation system. Let's try to write up this difference, finite difference formula for I equals 1, I equals 2, I equals 3, and just try to take the mystery out of it. So, for I equals 1, what do we have? Well, then we have C1 multiplied by Y2 plus A1 multiplied by Y1 plus B1 multiplied by Y0 is equal to H squared multiplied by F1. I'll just write f of xi as fi instead, just because it's easier and also because that's what they do in the book. Okay, and for I equal 2, we have C2 multiplied by Y3 plus A2 multiplied by Y2 plus B2 multiplied by Y1 is equal to H squared multiplied by F2. And for example, for I equals 3, we have C3 multiplied by Y4 plus A3 multiplied by Y3 plus B3 multiplied by Y2 is equal to H squared multiplied by F3. And so on until we get to I equal capital N, in which case I will have well, let's just start with I equal to n minus 1, just for fun's sake. Then I will have C n minus 1 multiplied by Y n plus C n, not C n minus 1, sorry, plus A n minus 1 multiplied by Y n minus 1 plus B n minus 1 multiplied by Y n minus 1 minus 1, which is minus 2, plus H squared multiplied by F n minus 1. And then for the last line, I have for I equal to n that the equation given is Cn multiplied by Y n plus 1 plus A n multiplied by Y n plus B n multiplied by Y n minus 1 equals H squared multiplied by F n. Now we want to be able to change this system into a matrix system. First of all, what is the reason for that? Well, what we know based on our boundary conditions, what we know is that what we know is that Y0 is equal to alpha, right? And we also know that YL, not YL, but Yn plus 1, that Yn plus 1 is equal to beta. And since we know that, what we now have is we have this and we have this, we want to use all of this knowledge to find some kind of finite difference solution for y0, y1, y2, and so on. But that's kind of hard, because if I just plug alpha in here, then I still can't find y1 because I need to have y2. And if I just plug beta in for this value, then I still can't find what yn and yn minus 1 because they're both unknown. However, this problem is not harder than the problem we sometimes have where someone tells you y plus x equals 2 and x minus y equals 4. Find x and y, because then you say, aha, I can solve that because I know how to solve two equations with two unknowns by considering them, one at a time, or by using some kind of matrix equation to do that, or by representing the coefficients as a matrix and then solving. So that's what we will do here. We will write this up as a matrix equation. And how do I do that? Well, first of all, the y. The y will be, the first question that we could probably have is, well, it doesn't really make sense to write y0 in here because I already know what y0 is, and I also know what yn plus 1 is. So maybe it's best if I just write y1 and so on down to yn. And then here I have the equal sign, and then I have our right-hand side, which seems, well, it seems pretty straightforward. It more or less feels like I just have to write, well, this is equal to h squared multiplied by f1, and then h squared multiplied by f2, and so on, all the way down to h squared multiplied by f begin. Well, that's almost the case, because in the first equation and the last equation, there is something special. This term is equal to b1 times alpha, because I know the value of y0. And because of that, I do not have any matrix coefficient that I can represent this by using a matrix A that I will draw up here in a second. So what I have to do is I have to move this over onto this side, which then gives me h squared times f1 minus b1 times alpha. And then all of these, h squared times f2, etc., hi times fi, and so on, they're just all fine until I come down to the last one, which, well, here I have the same problem because I do not have, well, sorry, I marked the wrong one. Here, I do not have any yn plus 1 in my y vector, and actually I know the value here. This is just beta. So I move my cn times beta over onto this side. So here I have minus c capital N times beta. That's great. Okay, so this is my vector z, and this is my vector y. Now I just need my matrix A. And I will leave this to you because for a YouTube video this can't go any longer. So look at 221. So this is a small exercise, and figure out how these coefficients C1, A1, C2, A2, B2, and so on, how they fit into this matrix by considering the expression for A in 221.